Okay, so it's really great to have Witten for his third lecture. He'll tell us about background independent algebra in quantum gravity.
Thank you. Before I get started, I just want to mention I misplaced a shoulder bag I was carrying around, black, shoulder, with a strap. So if anyone happens to notice it, please let me know. So roughly speaking, the aim today is to discuss an analog with gravity of the things that we've been discussing earlier in the week without gravity. So one thing we know is that in ordinary quantum mechanics, we usually consider the observer to be outside the system that's being observed. That's problematical in the presence of gravity because the observer inevitably gravitates. The problem is most obvious in the case of a closed universe. No one can look at a closed universe from outside. So in the case of a closed universe, which might be the real world we're living in, you have to envisage an observer in the universe that's being observed. Now, as discussed by some of us in the last few days, in ordinary quantum field theory without gravity, we can pick an arbitrary region U in space-time and define an algebra of observables in region U. So I've schematically drawn this here. M is space-time, and U is an arbitrary region that we picked. Now, there are problems with this in the presence of gravity. First of all, with space-time fluctuating, in general, it's much harder to explain what we mean by the region U in gravity than it is in ordinary quantum field theory. In ordinary quantum field theory, we can literally draw an arbitrary line on the map, or imagine an arbitrary imaginary line in space-time. In gravity, there has to be some invariant meaning. For example, the exterior of a black hole horizon is invariantly defined, but we need to consider something like that in the presence of gravity, not an arbitrary region. But there's a more fundamental question. Why do we want to define an algebra unless it's the algebra of observables available to someone who lives in the space-time? In ordinary quantum field theory, when we do this, we're imagining an observer outside the space-time who's probing the space-time but only in the region U. Why the observer does that is up to that person. But in any event, the laws of quantum field theory allow us to envisage what could be done by an observer who has that capability and no further capability. In gravity, the only analogous thing to do is to define an algebra that describes measurements that can be made by an observer who lives in the space-time. So I want to construct an algebra that describes measurements made by an observer. I'll assume the observer knows the laws of nature but has no knowledge of the state of the universe except whatever is learned from observation. So the second part, of course, fits us. We know nothing except what we learn by looking around. But the first part doesn't, because in the last few centuries we've been using our observations to learn the laws of nature as well as the state of the universe. So why do I make the stronger assumption that why do I assume the observer knows the laws of nature? Well, one reason is that it would be much harder to model an observer who's trying to learn the laws of nature. So pragmatically, I do what I can do. But I actually believe there's another reason, which is I think if we want to get the Bekenstein-Hawking entropy, we in fact have to consider the model I will consider of an observer who knows the laws of nature but doesn't know the state of doesn't know anything about the state of the universe. Anything the observer knows about the state of the universe would subtract from the entropy that you can gain by further observations, and lack of knowledge of the laws of nature would also subtract from what you can learn, since the entropy is roughly what you could learn by further observations. If we want to get the Bekenstein-Hawking entropy, we need to make assumptions that will maximize it. So, as I said, the algebra... thank you. Thank you. So, as I said, the algebra will depend on the laws of nature, but it's required to be universal and background independent, meaning it's defined once and for all without any knowledge of the specific space-time in which the observer is living. For example, if there's a landscape of vacua, many possible vacua, you don't know until you look around which one you're living in, and the algebra is supposed to have operators that distinguish the possibilities. So different spacetimes are supposed to correspond to different representations of the same algebra. Now, there's some, well, unfortunately I made this list of papers some time ago, so it's not really up to date. But regardless of what other papers there are, the one which is most significant for backgrounds is this one. But then the paper I'll actually be talking about isn't in this list, but it has almost the same title as the lecture. Something about a background independent algebra for gravity. Now, we expect that in a full theory of quantum gravity, an observer can't be introduced from outside, but has to be described by the theory. So what it means to assume the presence of an observer is that we define an algebra that makes sense in a subspace of states in which an observer is present. We don't try to define an algebra that makes sense in all states for two reasons. One is we don't know how to, and the second is we can't see what good it would be if we could define it. Of course, those two facts presumably go together. Presumably, we can only define algebras that are useful that describe something. Well, first let's describe the situation in the absence of gravity. The observer propagates in a spacetime M on a geodesic gamma. Well, I don't have to assume a geodesic. It's just the simplest model I can assume. In the absence of gravity, I could pick an arbitrary curve in spacetime and say that's the observer's world line. In the presence of gravity, I can't do that. I need some dynamical law that determines the world line. The simplest is to assume that the observer travels on a geodesic. We could make a more complicated model. For example, if there's a scalar field phi, we could assume that the gradient of phi exerts a force on the observer and the world line accelerates according to the gradient of phi. Or we could do anything else we want to do. But we need some law, and I'm just going to assume the simplest one, that the world line is a geodesic. The world line can be parameterized by proper time tau, but an important fact about proper time is that although there is a well-defined proper time difference between two points on the world line, there's no natural zero of proper time. And the absence of a natural zero of proper time will be important in a moment. Now, as in classic work, going back at least to Unruh, we assume the observer measures along gamma quantum fields, such as a scalar field phi, or the electromagnetic field F mu nu, or the Riemann tensor R mu nu alpha beta, as well as their derivatives in normal directions. I don't consider the derivatives in tangential direction along the world line, because since we already accept observables at any point on the world line as part of what the observer can measure, derivatives along the world line added nothing new, but normal derivatives do add something new. So we include those as observables. Now, I want to take some time to explain why this model actually makes mathematical sense, at least in ordinary quantum field theory, and I believe also in perturbative gravity at least. An elementary but not so well-known fact is that smearing a local field along a Timelike curve is indeed sufficient to define an operator. But by the way, one reason I'm going to go into this is that yesterday we ran into something that wasn't an operator, but that assertion caused some confusion. So I do want to spend some time to explain what we have to do to quantum fields to make operators. And that will clear up what we had yesterday, but it will also make it clear that the model in which we simply model the observer by a world line does enable us to define true operators. So, but anyway, because of this elementary fact that I'll explain in a second, there does rigorously exist an algebra of operators defined by smearing along a Timelike world line, and in the absence of gravity, will even tell you what that algebra is. By contrast, smearing in space is not effective at defining an operator, except in favorable cases where phi has rather low dimension. As an important special case of this, it's not possible to define an operator by smearing a local field on a cut of a black hole or cosmological horizon. We'll see exactly why that is in a second. So, first of all, the reason that smearing is necessary is very simple. Let omega be a Hilbert space state, such as the vacuum, and let phi of x be what we usually informally call a local operator. Then phi of x times omega is never a Hilbert space state since its norm is infinite. So, for example, phi of x can't have eigenvalues. If it had an eigenvector, that by definition, an eigenvector would be a state such that phi of x acting on that state remains in Hilbert space, being multiplied by the eigenvalue. So it must be that we can't measure phi of x, because the textbooks tell us that if we could measure phi of x, the answer would be an eigenvalue. But as I've just told you, phi of x doesn't have eigenvalues. That's why when you studied quantum mechanics, nobody helped you compute the eigenvalues of a local field 5x. They don't exist. Now, does smearing in spatial dimensions help? And we'll take d spatial dimensions, which could be all of the spatial dimensions, or maybe a subset, if we were interested in a cut of the black hole horizon. Well, smearing in spatial dimensions only help if phi has rather low dimension. So, for example, we let f of x be a smooth function of compact support, so a smearing function, but supported in space at time 0, although I didn't write that explicitly. And then by phi sub f, I mean the smeared operator. And then we want to know whether phi of f acting on a Hilbert space state remains in Hilbert space. So we have to compute the norm of phi of f1 omega, which is this. And it's given by this smeared two-point function of omega. And now, for example, suppose we have a theory that in the ultraviolet is conformally invariant, and that phi has dimension delta as measured in the ultraviolet. Then the most singular term in the OPE is x minus y to the minus 2 delta, and you see the integral converges if and only if 2 delta is less than d. So, for example, QCD in the real world is a theory where this condition can't be satisfied. In QCD, the maximum spatial dimension is 3, and the minimum delta of any gauge invariant operator in QCD is also 3, corresponding to a quark bilinear. So this is an example in which 2 delta is always bigger than d. In fact, 2 delta is at least d plus 3. So no operator can be defined by smearing in spatial directions. You could ask whether it would be better to work in Euclidean space and smear in Euclidean space in defining an operator. That would replace little d by d plus 1, and the inequality would be that 2 delta should be less than little d plus 1. And in QCD, it would still be violated. So in QCD, we also can't define an operator by smearing in Euclidean space. Now, a typical example of this phenomenon came up yesterday. We ran into the Lorentz boost generator, but integrated only over the half space x positive. And I made the assertion that it wasn't well defined as an operator. This is a typical example of what I just said. In dimension d, t00 has dimension delta equals d plus 1. So 2 delta is 2d plus 2, which is bigger than d. So we shouldn't be surprised that kr does not make sense as a Hilbert space operator. From this point of view, you might ask, why is the full k obtained by integrating over all space a well-defined operator? And that's actually rather special to the fact that it's a conserved charge. So conserved charges are better than the generic case. But anything that isn't a conserved charge behaves, as far as I know, anything that isn't a conserved charge behaves generically by the counting we just gave. Well, yeah, I think so. Okay, there's some fine print about that statement, but you'd have to work pretty hard to run into an exception. Now, from what I've told you, smearing in space is a very inefficient way to try to make a there is something I wanted to tell you. Sorry. Okay. This inequality 2 delta less than d is interesting. So in d dimensions, suppose we, for example, we look at the eternal black hole. Can you see the blackboard in the dark? Yes? Okay. So then we have the two horizons of a left and right observer, and they intersect at a particular cut of the horizon. I could consider for what I'm about to tell you any horizon cut. But this particular one is interesting, so we might as well consider that one. Now the dimension of a horizon cut is d minus 1. So in d space dimensions, a horizon cut has dimension d minus 1. So the inequality we need to define an operator is that 2 delta should be bigger than d minus 1. 2 delta should be less than d minus 1. So delta should be less than d minus 1 over 2. But there's a fundamental unitarity bound that says that that condition is impossible to satisfy. The minimum value of the dimension of a scalar field is precisely d minus 1 over 2. So a free field has dimension d minus 1 over 2, and by a well-known argument, that's the minimum dimension of any operator. So this condition can't be satisfied, although you can come arbitrarily close in general. In the sense that you can achieve the value d minus 1 over 2 so that there would only be a logarithmic divergence here. But you can't get rid of the logarithmic divergence. So you can, that was for a scalar field, but fields with spin are only worse. So you can't define operators on cuts of horizons. If you could define them, this would be extremely important in black hole physics. For example, you'd expect operators that you could actually define on a horizon cut to be central, since they would be accessible to both left and right observers. Operators at the intersection of the horizons of left and right observers would be potentially accessible to both observers. But that kind of thing doesn't work because of what I've just explained. It's special to relativity that it doesn't work. If you consider a non-relativistic quantum field theory, you could add higher spatial derivatives of a scalar field without higher time derivatives. We don't want higher time derivatives because they would spoil unitarity, but higher space derivatives, of course, break relativity, but they improve the ultraviolet convergence. And a lot of things I've told you, including this assertion, would not be true in the case of a non-relativistic field theory. So anyway, going on, I've explained that smearing in space is very inefficient. Actually, let me pause for questions about this. Okay, I don't see takers, so I'll go on. Now, although smearing in space is very inefficient for making true operators, smearing in time does make a true operator regardless of the value of the dimension. This was actually first proved by Borchers in about 1964, although I found the paper has very few citations, and I don't think the result is terribly well known. I will explain it informally. He gave a rigorous proof in algebraic quantum field theory, but I will just assume the OPE. So the Feynman epsilon is crucial. As I've explained, as I already used, the leading singularity in an OPE is a power of t minus t prime, but now I include the I epsilon, and delta is the dimension. And the series has lower order terms which are still singular, but they're less singular than this leading term, and they would be analyzed the same way. So now I want to define an operator by smearing only in time. Previously we smeared only in space. Now we're going to do the opposite and smear only in time. So at a fixed value of x, I take a smearing function f of t, a smooth function of compact support in time, and I smear this local field 5x and t by this function of t and integrate over t. But I'm only integrating over t. I define an operator that lives at a particular x but at a fixed value of t. Now the norm of the state given by phi f of x acting on the vacuum is given by this thing, or more exactly by its limit as epsilon goes to 0, which I didn't write explicitly, plus similar but less singular terms from higher order terms in the OPE. Now, it's obvious this is finite for positive epsilon, but I want to prove that it remains finite as epsilon goes to 0. And this actually has a kind of trivial proof. We write t minus t prime minus I delta minus I epsilon to a negative power as a derivative with respect to t, multiple derivative, of a higher power of t minus t prime minus I epsilon times a coefficient Cn that depends on n. In writing this, I assume 2 delta isn't an integer. If it is, the formula contains a logarithm. So inserting this formula, inserting this in the integral we're trying to analyze, we get this one. And then we integrate by parts n times with no surface term because f has compact support. And we arrive at this formula, which is obviously convergent as epsilon goes to 0. I wrote that for sufficiently large n, it obviously is finite as n goes to 0, but that was meant to be as epsilon goes to 0. For sufficiently large n, this integral converges as epsilon goes to 0, which we were showing that the left-hand side is finite. So we've learned that although smearing in space is a very inefficient way to produce true operators, that, for example, in QCD is a typical theory in which it doesn't work. But smearing in time, in any theory, universally always produces true operators. The operators you get this way are densely defined unbounded operators. That means they acting on a dense set of if assuming phi was a Hermitian scalar field, such an operator will have eigenvalues, but you could measure it. It would have eigenvalues that you could measure potentially, or at least the general laws of quantum mechanics say you could measure them, but they're unbounded above and below. And that means that it only acts well on a dense set of Hilbert space states. When I was lecturing earlier in the week and trying to keep things as informal as possible, I was occasionally getting questions about whether we didn't want to make bounded operators so that we would have a von Neumann algebra. If we want to do that, we have to take a bounded function of this guy. So we would have this phi sub f, and something like the exponential of I times phi sub f would be a bounded operator. Or more generally, if g is any bounded function of a real variable, g of phi of f would be a true bounded operator defined on all Hilbert space states. For today's lecture, that's not very important. It'll barely enter it. Well, I'll try to hide it, but it would have potentially barely entered at one point later on, but it's not very important. But questions that headed in that direction were asked by a few people in my first two lectures. So I thought I should address that at least briefly. So what we've learned is that it is indeed possible to define operators smeared along a time-like world line, and they can be multiplied without any trouble. So I showed that acting on a Hilbert space state phi f keeps you in Hilbert space, but then you could act with another phi g and another phi h. And a generalization of the same calculation will show that these truly form an algebra. You can keep going, acting with as many of them as you want. The technical terminology is that they have a common dense domain. These are unbounded operators with a common dense domain. Okay. Next, I'm going to tell you a little bit about what this algebra is, at least in the absence of gravity, but maybe I'll stop here if there are any questions. Yes?
So, the OPE, when you did the time smearing,
yes,
at least at first glance, very similar to the OPE with the spatial.
yes, but in space there's no I epsilon. The I epsilon saved us in time, but if you smear in space, there's no I epsilon to the rescue.
What happens if you consider smearing the fields with space with fields with functions whose support is an space-time region?
Well, the question is, what happens if we smear both in space and in time? Smearing in time was enough, and smearing in space doesn't make things worse. So you can smear in space-time, and that's the way things are often stated. But although this fact goes back to Borcher's half a century ago, and it's certainly known, the not so well-known fact that I've been explaining is that smearing in space has nothing to do with it. It's only smearing in time that's effective. Any other questions? Yes?
In the previous picture, shouldn't if the n goes to lambda, epsilon goes to 0? No, one ahead.
There was a misprint. I said n goes to 0 when I meant epsilon goes to 0. This should have been epsilon goes to 0. Yes. Any other questions?
When you talk about
I'll cut to you soon. Yes, go ahead.
when you talked about this inequality for the in the black hole, in the cut of the black hole.
Yes.
That was with space smearing, right?
Yes. We took a horizon cut. A horizon cut. The horizon is a null hyperplane. What's usually called a cut of the horizon is a codimension 1 space-like slice of the horizon. So it's a spatial submanifold of dimension little d minus 1. And I showed that you can never make an operator by smearing in little d minus 1 dimensions.
If that doesn't work even if you smear it in time.
Well, if you smear in time, it would work, but the horizon doesn't have a time direction. The horizon has a null direction. You're actually asking a good question, which is whether smearing in the horizon in a null direction helps. I'm forgetting something, but I think the answer is only in free and supernormalized, only in very favorable cases. But I'm forgetting slightly. Sorry. The issue was discussed by Aaron Wall in his famous paper on the generalized second law, but I'm drawing a blank at the moment. Yes?
In this case, I had a feeling that the day saved by the Feynman prescription.
The what prescription?
The Feynman prescription, the I epsilon.
For smearing in time, the Feynman I epsilon saved us.
Can we see this as a sort of IR regularization, infrared regularization?
It's more like a UV regularization because the UV was the problem. So at t equals t prime, there was a singularity. The I epsilon told us how to go around that singularity. And for the purposes of what we're doing here, the recipe has a limit as epsilon goes to 0. Yes?
Is there an intuition between the smearing in time, between time and space? Because smearing in space looks like having a force grain or something like that, and maybe time is pretty different.
Well, the I epsilon is like a little bit of imaginary time. And propagation through imaginary time gives very strong damping. So, in time, things are highly oscillatory. And it's subtle that this calculation worked with smearing in time. It's because it's subtle that I spent the time to explain it. And so that you'd appreciate it, I wanted to show that smearing in space did not work. And also, although I didn't write it out in detail, smearing in Euclidean space-time does not work either for the same reason, except with little d replaced by little d plus 1. But I was surprised when this was first explained to me, which was by Arthur Jaffe, perhaps a decade or so ago. Although, as I've told you, it wasn't a new result. It was known before I went to graduate school, but anyway, I spent most of my life not knowing about it. I don't know what else to tell you. One other fact I can tell you is that not only does Borcher's original paper not have many citations, but it's surprisingly hard to find it online. I had to work fairly hard at that. Of course, he didn't prove it with the OPE. He proved it from the Whiteman axioms. So his argument was more general. I gave a sort of informal explanation using the leading term in the OPE. So we've learned that it's possible to define an algebra of operators smeared along an arbitrary time-like world line. But what is this algebra? This question is answered by the Timelike tube theorem, which is a close cousin of what's called HKLL reconstruction in ADS-CFT duality. HKLL is a kind of, well, perturbative version adapted to the special situation of ADS-CFT. In quantum field theory without gravity, the algebra of operators along a time-like world line gamma is actually equivalent to the algebra of operators in a certain open set E of gamma. So if gamma, the time-like world line could be infinite, but here I've drawn a finite one. So the blue line is a finite time-like world line, starts here, ends here. And the red region is called the time-like envelope of gamma, of the world line gamma. It consists of all points that you can reach by deforming gamma through time-like curves, keeping its endpoints fixed. So in Minkowski space, that fills out the time, what's called the causal diamond of the initial and final points. In a general space-time, it can be more complicated. It's actually not known in general. There's some things about this that aren't known, but I won't go into it. So in the absence of gravity, the algebra of gamma of operators along a time-like geodesic gamma is equivalent to the algebra of operators in a certain open set, namely the time-like envelope. In my opinion, that makes A of gamma as a reasonable substitute for the algebra of a region. Without gravity, the algebra of a region is a good notion. With gravity, unless we can talk about the region in some invariant way, it's not such a good notion. And anyway, with gravity, something is not well motivated unless it's actually the algebra of operators that somebody can measure. So what I think is well motivated with gravity is to make a model of what someone can measure, and that's what A of gamma is meant to be. So A of gamma seems better motivated in gravity than the algebra of a region, but it's encouraging that without gravity, and I believe also in the context of perturbative gravity, A of gamma actually is equivalent to the algebra of operators in a certain open set. I'm saying perturbative gravity because in perturbation theory, gravity is similar to another quantum field. Non-perturbatively it isn't. Space-time fluctuates, topology changes. Space-time might be purely emergent and not well defined. We don't know what happens in gravity non-perturbatively. But I presume that perturbatively gravity is another quantum field, and therefore that this kind of statement is also valid perturbatively in the presence of gravity. Now, to understand more concretely what is A of gamma in the presence of gravity, let's focus on a particular observable. Say we have a scalar field phi, and we consider phi evaluated at x of tau. Tau is the observer's proper time, and x of tau is the position of the observer at proper time tau, and then phi of x of tau is an observable that the observer can measure at proper time tau. I'll just abbreviate it as phi of tau with x of tau understood. So without gravity, we would just say that the observer can measure phi of tau for any tau. When we take gravity to be dynamical, there's an important difference. We have to take seriously diffeomorphism invariance. Well, we have to consider the fact that the same world line can be embedded in a given space-time in different ways, differing by shifting tau by a constant. So part of the fact that the observer knows nothing about the space-time is that even if you specify the space-time and the world line that the observer has, there's no natural zero of proper time. Or if the observer has defined a zero along the world line, that could be anywhere in space along the embedded line. So when you think about the world line in the presence of gravity, you should think of it as having a one-dimensional metric that enables you to compute proper time differences, but there's no natural zero of proper time. So a way to think about that is that there would be a diffeomorphism of the whole space-time that maps gamma to itself and preserves the metric along gamma, but moves gamma forward in proper time. And that's an example of a diffeomorphism, so we have to treat it as a constraint. Of course, we have to consider all diffeomorphisms of the space-time as constraints, but the ones that act trivially on the world line, well, the ones that map trivially on the world line, we can imagine we've already imposed as constraints. The interesting one from the observer's point of view is the one that maps the observer forward and world line forward in time. So phi of tau by itself isn't a meaningful observable with gravity. We need to introduce the observer's degrees of freedom and define tau relative to the observer's clock. So in a minimal model, we equip the observer with a Hamiltonian, which is a constant plus what I'll call Q, which makes up what I'll call the observer Hamiltonian, H observer, and a canonical variable P, which is minus ID by dq. However, it turns out that it's better and also physically well motivated to assume that the observer energy is bounded below, say that it's non-negative, so that m is the observer's rest mass. We then only allow operators that preserve this condition. So for example, we don't really allow the operator e to the minus ip, which does not preserve q being non-negative. We replace it by pi e to the minus ip pi, where pi is the projection operator onto non-negative q. So we'll freely write any operator we want, but we'll always put pi before and after. Now we only want to allow operators that commute with the constraint. I'll call the constraint h hat, where h bulk is any gravitational constraint operator that generates a shift of tau along the world line, and h observer is the observer Hamiltonian. In a general spacetime, there isn't a canonical h bulk, but any two of them differ by a diffeomorphism that acts trivially on the observer. And we imagine we've imposed all those as constraints. And once we've done that, it doesn't matter which h bulk we pick. And we're left with the one constraint that really has an interesting bearing on constructing the observer's algebra, and that's what I'm calling h hat. An operator that commutes with h hat is invariant under a spacetime diffeomorphism that moves the observer world line forward in time, together with the time translation of the observer system. Well, how do we find operators that commute with the constraints? Since h bulk commuted with phi of tau is minus I phi dot, since by definition of the fact that h bulk moves the observer forward in time, we need q with phi to be I phi dot. And we can achieve that just by setting tau equal to p, the canonical conjugate of q, or more generally, tau could be p plus an arbitrary constant s. So a typical allowed operator is phi of p plus s, except that we have to project it before and after with this projector pi. So typical allowed operators what I'll call phi hat s, which is pi times phi of p plus s times pi. In addition to these operators with phi possibly replaced by any other local field along the world line, there's one more obvious operator that commutes with h hat, namely q itself. So we define an observer algebra A sub observer that's generated by the phi hat s as well as q. Now this setup hopefully sounds background independent. Remember, the goal at the beginning was to define an algebra that depends on the laws of nature but not on any knowledge of the spacetime. So we're not allowed to make any mention of the background in which the observer is living in defining the algebra. And hopefully it appears like we've done that since we didn't mention anything about the spacetime. But there's a crucial detail. If you really want background independence, you have to interpret the formulas properly. We won't get background independence if we think q and phi hat s are Hilbert space operators. To get a Hilbert space in which they act, we'd have to pick a spacetime M in which the observer is propagating. And then we don't have background independence. To get background independence, we think of the observer algebra as an operator product algebra rather than an algebra of Hilbert space operators. The algebras for different m's are inequivalent representations of the same underlying operator product algebra. In the absence of gravity, we characterize the objects phi of tau by their universal short distance singularities. And that characterization requires no knowledge of the quantum state. After coupling to gravity and including the observer and the constraint, the short distance expansion in powers of tau minus tau prime becomes an expansion in powers of 1 over q. And we characterize the observer algebra purely by this expansion of operator products. An operator product algebra isn't an algebra. Not in the usual sense, or at least not in an interesting way. That's because operator product relations are only asymptotic. You never can multiply phi of x times phi of x prime and get something. You only get an asymptotic expansion of the something. So, although the term operator product algebra is traditional, it's not an example of an algebra, not in any non-trivial way. If you were to call it an algebra, it would be a completely stupid algebra with no non-trivial relations. So something very much like what I've just told you was done by Holland and Wald, sort of in the context of algebraic field theory. In the literature, people were struggling a little bit to explain what it meant to have the same quantum field theory on two different spacetimes. But Holland and Wald had the very sensible observation that the OPE expansion is independent. This was for quantum field theory in a given curved spacetime. So gravity isn't dynamical, but you want to explain what it means to have the same QFT in different spacetimes. they made the observation that the operator product expansion is independent of the spacetime as long as you allow the coefficients to depend on the Riemann tensor and its covariant derivatives, which I didn't have to tell you here because the Riemann tensor was one of the operators in the expansion. So I didn't have to tell you separately that it was allowed. For them, it was necessary to say that because the Riemann tensor was a C number. So if you allow the OPE coefficients to depend on the Riemann tensor and its covariant derivatives, then the OPE expansion doesn't depend on the space-time. And in their approach, what it meant to have the same QFT defined on different space-times is that in each case you had local operators obeying the same OPE algebra. I probably shortened that a little bit, but that's the basic idea. So, just as in the work of Holland and Mold, similarly here, since the OPE expansion is universal, if we interpret the observer algebra as an OPE algebra, it's background independent. So, any questions before I go on? Now, there's a very special case that turns out to be important. That's the case that M is an empty de Sitter space with some positive value of the effective cosmological constant. So I've drawn the familiar Penrose diagram of de Sitter space with the far future at the top, the far past at the bottom, and I've picked coordinates so that the observer world line is the left edge of the diagram, and the region causally accessible to the observer is the static patch that's drawn in green, which is bounded by past and future horizons as shown. So the green region is called a static patch because it's invariant under a particular de Sitter generator that I'll call H that advances the proper time of the observer. So I mentioned that in general there was no canonical choice of the constraint H that we use in defining the algebra, but in this particular example there is, the global symmetry. In the absence of gravity, there's a distinguished de Sitter invariant state that I'll call psi ds, often called the Bunch-Davies state, such that correlation functions in this state are thermal at the de Sitter temperature, TDS, which I'll call 1 over beta ds. Beta is 2 pi times the radius of curvature. Now, what does it mean to say that correlation functions are thermal? For the 2-point function, for brevity, I'll only state what it means for the 2-point function. The story for n-point functions is similar. For the 2-point function, the statement of thermality means two properties. One is just time translation symmetry. You might take the 2-point functions at different real times, tau and tau prime. Sorry. We're going to consider real time, well, since we're interested in observations along the observer's world line, tau is going to be, we're going to consider operators on this left edge, which is parametrized by tau, proper time along that world line. And then time translation symmetry just means that the real-time 2-point functions in the state psi ds are invariant under adding a constant to tau and tau prime. And the deeper aspect of thermality is called the KMS condition. And it says essentially that, well, of course, 2-point functions depend on the ordering of the operators because operators don't commute. But the claim to fame of a thermal correlation function, a thermal correlation function is a trace 1 over the partition function, a trace of each of the minus beta h times the product of the two operators, phi of tau, phi prime of 0. Phi and phi prime are different operators. Because it's a trace, you can try to move phi all the way through the trace to get to the other end and get a formula that relates the traces in different orders. But when you do that, you have to pull it through each of the minus beta h. And since h is the generator of time translations, and here we have each of the minus beta h, which is time translation by an amount minus I beta, when phi comes back on the other side, it's shifted in imaginary time by minus I beta, which gives this relation. So this is essentially the KMS condition, except to state it carefully, you have to talk about holomorphy in a strip, but I won't bother with that. But the KMS, well, I'll just say that the KMS condition says, if you take this thing and analytically continuate in tau and also this one, then they satisfy, the continued things satisfy this relation. Well, that's still that's still not the best statement, but we'll live with it. Anyway, this is meant to be a thumbnail review of what happens in the absence of gravity. In the absence of gravity, we have thermal correlation functions in the natural de Sitter state psi ds, and thermality means time translation symmetry and also this KMS condition. Well, when we include the observer and gravity, we have to extend the state psi ds to include a state of the observer. And there's a nice one where we give the observer energy a thermal distribution at the de Sitter temperature. So the nice state is this one. I'll call it psi max, where the reason for the subscript max will be clear in a bit. Psi max is the de Sitter state times an observer wave function. The square root is a normalization condition, so that's a normalized state. And psi squared is e to the minus beta. So the factor e to the minus beta q over 2 is appropriate, so that psi squared gives a thermal distribution at the de Sitter temperature. So in the presence of gravity, we consider the algebra I told you about before. We replace phi of tau by its gravitationally dressed version, but we also replace psi ds by the state psi max. And now something nice happens. A straightforward computation shows that the properties 1 and 2 have analogs. So property 1 was time translation symmetry, and it still has an analog, but now what's shifted is the index s and s prime. So time translation symmetry becomes a statement. The shifting s and s prime by the same constant c is a symmetry. I see a misprint. This prime here shouldn't be there. It's phi times phi prime, and here it should again be phi times phi prime. And the second thing, which is the main point actually, is that the KMS condition simplifies. The usual KMS condition has a shift in imaginary time because of going through the e to the minus beta h in the trace. But the modified KMS condition with gravity and the observer included has no such shift and just says that you can exchange the order of the operators with no change in the correlator. The proof is really quite elementary. Well, I've actually written a couple versions of the proof, but the simplest is in the paper that has almost the same title as the talk. The proof is a very simple contour integral manipulation. Now, what is the significance of this modified condition 2 prime? It says that if for any element of the observer algebra, we define the expectation value of A in the state psi max to be what I'll call trace of A, then the function trace does have the algebraic property of a trace. The trace of AB equals the trace of BA for any A and B in the observer algebra. This function also has the property that the trace of A dagger A is strictly positive for all non-zero A, which is described by saying that it's non-degenerate. Non-degenerate means that for every A there's a B where the trace is not 0. And in fact you can pick B to be A dagger. So this is a non-degenerate trace. And moreover, assuming psi max was, assuming psi ds was normalized, we arranged this factor so that psi max is normalized. And therefore, our trace has the property that the trace of the identity is 1. So I've called this function the trace, which is in fact traditional in operator algebra theory, because it has the crucial algebraic property of a trace. But it's not the trace of any Hilbert space representation. The trace of this algebra in any Hilbert space representation is actually infinite. The trace of, for example, the trace of the identity operator in any Hilbert space, the conventional trace defined as a sum over states of an element of this algebra in any Hilbert space representation can be shown to be infinite. So this is not a trace in any representation, but it is a function on the algebra that has the algebraic properties of a trace. And we can use it the way we're accustomed to using traces because it satisfies the axioms of a trace. Now, let H sub ds be the Hilbert space that we get by quantizing fields in de Sitter space to all orders of perturbation theory, or of gravitational perturbation theory. Really, we could work exactly in the other fields, but I guess we'd better treat gravity perturbatively. Let psi be any state in this Hilbert space, and consider the function that takes an element of the algebra to its expectation value in the state psi. Roughly speaking, because the observer algebra has a non-degenerate trace, we can expect that there is a density matrix rho in the observer algebra such that the expectation value of A in the state psi will be the trace of A times rho. And we then call rho the density matrix. And we might expect that, as in ordinary quantum mechanics, the density matrix will be a positive operator of trace 1. Well, let's show that, well, let's discuss if it's true that all states have density matrices. So to begin with, let's find the density matrix of the state psi max. Well, the definition of the trace makes it clear that the density matrix of the state psi max is what I'll call sigma max, which is 1, because the condition it's supposed to obey I'm not seeing the same thing here that you're seeing. Sorry. Has that been happening throughout? Okay. Well, I hope it hasn't been happening throughout, because you would have been quite confused. I don't know what just happened. Okay. The property that the density matrix of the state psi max would have is that for any operator A in the algebra, the expectation value of A in the state psi max should be the trace of A times sigma max. But the trace of A times sigma max is, by definition, the expectation value in the state psi max of A times sigma max. So the property we want is that this should equal this. And the operator that satisfies it is obviously that sigma max should be the identity. So the density matrix of sigma max is 1, somewhat analogous to a maximally mixed state in quantum mechanics, whose density matrix is usually a multiple of 1. Here we actually have 1 with the way we've normalized the trace. So, as we'll see in more detail, psi max is maximally mixed, like a maximally mixed state in ordinary quantum mechanics. So we found the density matrix of one state. Now let's find the density matrix of a bunch of states, namely the state psi A, which is A acting on psi max, for any A in the observer algebra. Well, I claim its density matrix is A dagger, because for any B in the algebra, the expectation value of B in the state psi A is this by definition of psi A. And then by definition of the trace, that's equal to this. And by the cyclic property of the trace, that's equal to this. So we've discovered that this equals this, which tells us that A dagger is the density matrix of psi A. So we've discovered that every state of the form A times psi max for any A has a density matrix. But the states psi A are dense in the Hilbert space, essentially by the Riesz-Leiter theorem, which was the topic of the first lecture. So a dense set of states have density matrices. If we want all states to have density matrices, we need, rather than just a dense set of states, we need to take a useful further step. The Hilbert space is actually the closure of the dense set of states A on psi ds. So if we want every state in HDS to have a density matrix, we have to similarly take a closure of the algebra. And this closure is no longer background independent. It can be defined as the von Neumann algebra generated by the bounded operators in the observer algebra, or bounded operators of functions in the observer algebra. I'll call the closure the observer algebra in de Sitter space. See, the observer algebra as an OPE algebra was universal, but to take its closure, we had to have a Hilbert space representation in which the things were acting. And then the closure depends on the space-time. So now the observer algebra becomes a Hilbert space algebra, an algebra of operators, but it's no longer universal. It is true, though, that in this closure of the algebra, every state in Hilbert space has a density matrix in the closed algebra. And this step is the only step where, at least in today's lecture, it's useful to discuss von Neumann algebras. So any questions? Yes?
You can use time to define a conservation law for energy because in the sitter there are no conservation of energy in global de Sitter.
Yeah, there's no conservation law because the symmetry operator was a constraint. So it annihilated physical states and commuted with physical operators. So we didn't actually discover a conservation law. All we defined was an algebra of observables accessible to the observer. Any other questions? Okay. Now, let's recall that Bekenstein and Hawking discovered that one should attribute an entropy to a black hole horizon, and not long after, Gibbons and Hawking suggested that one should also attribute an entropy to a cosmological horizon, such as the horizon experienced by an observer in de Sitter space, which actually was their main example. So they said that A over 4G, where A is the area of any of these horizons, which in the particular case of de Sitter space are all equal, in some sense was the entropy of de Sitter space, which in their words, and this is almost a precise quote from the paper, they claim or conjectured that it captures the ignorance of the observer about the regions that the observer can't see. That was the interpretation they proposed. Another possible interpretation is that it captures the amount of information the observer could potentially extract about the state. However, a microscopic interpretation of the entropy of a cosmological horizon has been obscure, even compared to the black hole entropy, whose interpretation we also don't understand nearly as well as we would like. But we can now give a partial answer to this question, at least for perturbative gravity in de Sitter space. Once we know that every state of the observer algebra has a density matrix, we can define entropies as well. The von Neumann entropy of a density matrix is, as usual, minus the trace of rho log rho. And we can use that definition here. Well, what's going to happen if we use that? Well, in ordinary quantum mechanics, a maximally mixed state has a density matrix that's a multiple of the identity, and it has the maximum possible von Neumann entropy. The analog here is the state psi max, whose density matrix, the way I defined it, actually is the identity. And that suggests that it might have maximum entropy, which actually is true. It's clear that the entropy of the state sigma max, as defined as I have, is minus the trace of 1 log 1, which is 0, because the logarithm of 1 is 0. And by imitating a proof that in ordinary quantum mechanics you show a maximally mixed state has maximum entropy, you can prove that every other density matrix has strictly smaller entropy, negative entropy. One way to make the proof is as follows. Let rho be any density matrix other than the identity, and then consider interpolating from 1 to rho by this family of density matrices. And let f of t be the entropy of rho sub t. So it's this. So s of rho is f of 1. And then f of 0 is 0, because that's the entropy of 1. And then it's almost immediate that f prime of 0 is 0. And that f double prime of t is negative for all t follows by this little calculation, which I think I'll leave you to think through later if you want to look at the slides. And since f of 0 is 0, f prime of 0 is 0, and f double prime is negative, we learn that f of 1 is negative, so s of rho is negative. So that proves that empty de Sitter space with the thermal distribution of the de Sitter entropy was the state of maximum entropy by this definition. So an observer, a different way to say it is what I wrote here. The system consisting of an observer in the static patch has a state of maximum entropy, which is the natural de Sitter invariant state times this special observer state where the observer is in thermal equilibrium with the background. And that's a state of maximum entropy. So why did this turn out to be a state of maximum entropy? The original argument that empty de Sitter space has maximum entropy goes back to a relatively old paper of Busso, who, with absolutely no microscopic definition of entropy, proposed that this must be true purely on thermodynamic grounds. He observed, forget the observer world line because there wasn't an observer in Busso's treatment. With probability 1, any particle or field in the static patch leaves it through the future horizon eventually. So the static patch spontaneously evolves to be empty in the far future. And then Busso says that whatever happens spontaneously must be increasing the entropy. And since any system evolves, any initial state of the static patch evolves spontaneously to be empty, it must be that the empty state of the static patch is maximizing the entropy. So Busso gave that argument purely on thermodynamic grounds with no microscopic definition of entropy. Here it's slightly modified. We've defined the static patch by the presence of the observer, so by definition the observer never leaves the static patch even in the far future. But it's reasonable to expect that in the far future the observer is in equilibrium with the quantum fields and that the static patch is empty except for the presence of the observer. So adapting Busso's argument to our situation, psi max is what you would expect to be the maximum entropy state. So the maximum entropy state we found is the one suggested by Busso's argument. In a more general space-time, I don't know an equally explicit definition of the entropy of a state of the observer algebra. But there's a fairly reasonable conjecture. Okay. I should say a couple things about this, first of all. So this definition, it was a microscopic definition, but it defined the maximum of entropy to be 0 rather than A over 4G. We want the entropy A over 4G according to Gibbons and Hawking. The trace that we defined was really a renormalized trace, and the renormalization of the trace amounts to an additive renormalization of the entropy. So what this definition really gave is entropy differences in a natural way. And you can actually show, and it is shown in the CLPW paper that I cited at the beginning, that if you consider a state other than empty de Sitter space, the entropy difference between that state and psi max is equal to the generalized entropy difference between empty de Sitter space and the state considered, by the usual definition of generalized entropy. So this definition of entropy, well, it's a microscopic definition that can be shown to agree with the expected generalized entropy for entropy differences, but it misses a crucial absolute constant in the entropy, which is the A over 4G term. The algebra does not have the information needed to give that constant term. We lost it when we arbitrarily normalized the trace so that the trace of the identity was 1. We didn't have any, if we normalized the trace so that the trace of the identity was e to the A over 4G, then we would have had the A over 4G as then we would have gotten the correct entropy, including the Gibbons-Hawking term. But we didn't have any algebraic justification for that. And so we simply normalized the trace so that the trace of the identity was 1. However, now I'm going to go out on a limb and use what's still the remaining 10 minutes to give a speculative general definition of entropy. The definition I gave was only for an observer in the static patch of de Sitter space. I'm going to give a speculative definition of entropy in general in an arbitrary spacetime. And it will include the A over 4G term. That's the good news. And it's conjecturally it's general. The bad news is that there isn't that much evidence for it. So the last 10 minutes will be much less precise than what I've told you until this point. We'll go out on a limb a bit. There's a somewhat reasonable conjecture which was inspired in part by Aaron Wall's work on the generalized second law, which I'd have loved to lecture about, but which time just didn't permit. But Aaron Wall interpreted, in proving the generalized second law, Wall interpreted the generalized entropy as a relative entropy between a state of interest and a distinguished state, which in that case was essentially the Unruh state, roughly, or Hartle-Hawking state. And that suggests doing something similar in cosmology, to interpret entropy as relative entropy with some special state. And if you ask what's the special state that's been suggested in cosmology, it's the no-boundary state. And not very much thought will show you that if you use the no-boundary state, you can get the A over 4G. So the idea is to interpret the Hartle-Hawking no-boundary state as a sort of universal state of maximum entropy. Now, well, there are a few motivations. The analogy with Aaron Wall's work is one, but another motivation is simply the following. Hartle and Hawking invented their state as a kind of generalization of the natural de Sitter invariant state. And since the natural de Sitter invariant state, in a sense we've discussed, has maximum entropy, that suggests that the no-boundary state has maximum entropy in some more universal sense. So the empty de Sitter space has maximum entropy among states in a particular de Sitter spacetime, as seen by an observer. And that makes us wonder if maybe the Hartle-Hawking no-boundary state maximizes the entropy more universally, where you're allowed to look at all possible spacetimes now. Now, the expectation value in the no-boundary state. I'm going to have to then assume that the no-boundary state makes sense. The honest truth is that our understanding of it is so primitive. We know almost nothing about the no-boundary state in general spacetime. I can't promise you it makes any sense, but I'll speculate about it anyway. Assuming the no-boundary state is well defined in a general spacetime, the expectation value of an operator in the observer algebra in the no-boundary state is a state of the observer algebra that I'll call sigma of A. So sigma is motivated by the fact that I use sigma max for the maximum entropy state in de Sitter space. Maybe I should have called this sigma no boundary. So then if A going to rho of A is any state of the observer algebra, then I suggest that the relative entropy between rho and sigma for the observer algebra gives up to sign a definition of the entropy of the state seen by the observer. So this is the proposed general definition of entropy in cosmology. Now, an important detail where my thinking differs from what it was in the paper of possibly 2 years ago is that we should not try to normalize the no-boundary state. Rather, we should just take the no-boundary state as it appears from the gravitational path integral. One reason for that is that it gives the right answer, as I'll explain in a second. So if we don't normalize the no-boundary state, then we will get the A over 4G. If we do normalize the no-boundary state, we'll get what I actually wrote in the paper, which is differences of A over 4G between different states in the landscape, but with an ugly overall additive constant, independent of the spacetime. Philosophically, there's another reason to not try to normalize the no-boundary state, which is that we don't know how to. Well, for one thing, there are some suggestions that the no-boundary state is actually unnormalizable. I suspect that might be the case. But even if it isn't, the observer living in a particular spacetime doesn't know how to normalize the no-boundary state. The normalization probably depends on the no-boundary state in some other spacetime the observer isn't living in. The observer might not know about that, but might be able to make some sense of the no-boundary state in the spacetime the observer is actually experiencing. So philosophically, I think in hindsight, it makes some sense to not try to normalize the no-boundary state, though I didn't have the wisdom to do that, to not normalize it 2 years ago. Now, the main evidence for the proposal beyond what I've said is that in the case of a de Sitter-like spacetime, it gives correctly the A over 4G term in the entropy. That's because you're again not seeing what I'm seeing. I wonder why. Okay. That's again because, well, the definition, remember, the proposal was that entropy is minus the relative entropy with the no boundary state. And the relative entropy in ordinary quantum mechanics is this. Let's accept that formula. I'm not worrying about nicety of operator algebras. We have a minus sign in front. So this is, in ordinary quantum mechanics, with the entropy plus the trace of rho log sigma. So this formula is actually, claiming that this gives the A over 4G term is a reinterpretation of the original calculation of Gibbons and Hawking. If we interpret sigma as the no boundary state in a de Sitter space where the area is A over 4G, sigma, according to Gibbons and Hawking, with the e to the A over 4G, so log sigma is the C number, A over 4G, and the trace of rho is 1, so this term would be the A over 4G, and this would be the quantum part of the entropy. Or if you like, this would be the entropy as defined algebraically in the lecture, up till now. And this is the term that we didn't have when we were working purely algebraically. So you might feel I cheated by not normalizing the no boundary state. And in the paper, I normalized it. So what does that do? Well, I assume we're in a landscape with many possible de Sitter invariant states with many different values of the cosmological constant. And if the no boundary state is normalizable, the normalization integral is probably dominated by the one with the smallest value of the cosmological constant. So then log sigma in a particular spacetime is A over 4G minus A over 4G of some other spacetime that minimizes the cosmological constant. So in that case, the formula would miss from Gibbons and Hawking by a constant independent of where we are in the landscape. That's actually the way I wrote it in the paper. But I've come to believe that normalizing the no boundary state was the wrong thing to do, both philosophically and also because an observer wouldn't know how to normalize it. Plus, current literature suggests that the no boundary state is unnormalizable, which is another good reason to not try to normalize it. Well, to some extent, I said in the paper, well, if you read my paper, you'll see I almost said there that it was unnormalizable, but okay, I got tangled. Beyond what I've told you, and apart from the analogy with the work of Aaron Wall, the main appeal of the proposal is that it might make sense universally in a cosmological setting. But the proposal only makes sense if it's true that the no boundary state is tracial for the observer algebra in every space-time. The reason is that this extra term here only can be, we'd like to interpret that extra term as a space-time dependent constant shift of the entropy. But that's only true to the extent that sigma is a C number in each space-time. Well, C number is an informal way to say it, a tracial state of the observer algebra. There isn't, well, it's not, it's far from clear if that's true, but some arguments to that effect were given in a recent paper that gives me a little bit of optimism, I guess. Okay, the reason we want the no boundary state to be tracial, I already told you. If it isn't, then this term wouldn't have a sensible interpretation as a contribution to an entropy. And that we need that last term because it's that last term that contributes the A over 4G term that the definition of entropy purely inside the algebra doesn't know about. Now, to finish up in just 1 or 2 minutes, because the chair probably has noticed I'm out of time. I'm afraid I didn't... 3 minutes? Okay. Well, we'll be okay within 3 minutes. A remark here is that it was an idealization to assume that the observer lives forever in the past and future, and it was also an idealization to assume that the observer can make arbitrary measurements. So it might be important for some purposes to make more realistic models of observers. And for example, I would certainly very much like to know what one should say about an observer who didn't always exist in the past, like us, or perhaps who won't always exist in the future. But I've come to suspect that we need to make these idealizations if we want to get an interpretation of the Bekenstein-Gibbons-Hawking entropy as the entropy of a state of the observer algebra. Entropy measures information that could be extracted in principle from the state. So if we make more realistic assumptions that restrict what information the observer can extract, we should expect that the information accessible to that observer is less, and the entropy we would define is less. So I've come to suspect that the highly idealized assumptions we made are actually the ones we should make if we want to get the Bekenstein-Hawking entropy as the answer. Now, all kinds of things are missing in this lecture, in this approach. Well, as I told you, we'd like to learn what to say about an observer or civilization that didn't always exist. I use field theory language. I'd like to know an analog in string/M theory. The presentation I've given is most interesting for an observer who can't see the whole universe, although it makes sense regardless, and that was actually important in the recent paper of Blomert, Kudler, Flamm, and Urbach. And finally, it would really be nice to get better justification for the claim that entropy in cosmology is minus the relative entropy with the no boundary state. Thank you.
Very much for the beautiful lecture. So it's time for questions.
So if one were to include quantum corrections to the no boundary state,
Yes?
how would one compute them? And should we take the sphere partition function as
Well, I know why you're asking, and I'm not going to be able to answer, unfortunately. The sphere partition function is somewhat problematical, as first shown by Preskill and more recently analyzed by Wan. And a very interesting recent paper, of Cutler and Jensen, thank you, well, has a perfectly common sense proposal for the norm of the no boundary state that makes sense, but doesn't agree with the partition function on the sphere for reasons that aren't that well understood, I don't think, certainly not by me. For the lecture, what we actually need for the lecture, well, okay, sorry, yeah, okay. For what we need for the lecture is for the expectation value of a state of the observer algebra in the no boundary state to make sense. What Cutler and Jensen did was to consider the no boundary state in the far future, where the computation of the norm was straightforward. And it kind of makes sense to do that here. We don't have to use, okay. I won't ultimately be able to answer your question properly, so maybe I should quit while I'm ahead. I'll just say that what we actually use about the no boundary state is that the expectation value of a state of the observer algebra in the no boundary state has to make sense regardless of the space-time. That's the property we need, and conceivably some other things that we don't need are not true. I don't claim to know anything. I don't claim to know anything about the no boundary state that isn't in the literature, and that's much less than we would wish. Any other questions?
Relatedly, are you thinking of the no boundary state as prepared by this Euclidean gravitational path integral to contain additional topology?
Well, the honest answer is I don't know what the no boundary state is. What I need is for the no boundary state to be a universal state that exists in every space-time and is tracial for the observer algebra in every space-time. I think my whole discussion only makes sense to all orders of perturbation theory for an observer in some space-time. If the space-time topology is fluctuating, the observer might not exist, and we would probably need a better language. I need the no boundary state to make sense to the extent that the lecture made sense. And what I really need about it is that it gives a tracial state of the observer algebra in a general spacetime. Let me point out two facts that to some extent agree with each other. In a general spacetime, it's very hard to see explicitly why the observer algebra has a tracial state. It's also extremely hard to see what the no boundary state means in a general spacetime. So therefore, it's hard to exclude the hypothesis that the tracial state is the no boundary state is always tracial. I apologize for the negative statements. The only positive claim in the literature you'll find is in this paper by these authors, and I don't really have time to explain their arguments, but you could look at the paper and see if you find it convincing. Any other questions?
A few slides ago, you computed the von Neumann entropy of the sitter state, and the result was negative. I was
Yes.
a little bit confused about it, because should not
Oh no.
von Neumann entropy be Positive.
In ordinary quantum mechanics, von Neumann entropy is positive. Here we've renormalized the trace. Okay, let me explain why that gives an additive renormalization of the entropy. The trace, if we had taken a Hilbert space trace, would have been divergent. So nevertheless, we were able to define a function with the algebraic properties of a trace, but we didn't know how to normalize it because it wasn't a counting of states. So let's discuss what happens if we had rescaled the trace. Well, we define density matrices like so. The right-hand side was well defined, but obviously if we rescale the trace, we have to rescale the density matrix. Now let's look at the entropy. Oh, thank you. Thanks. If we take if we do this to the trace and we do this to rho, you can see that the entropy is shifted by a constant, which is plus or minus lambda, plus lambda. So there was an additive renormalization in the entropy, and the algebraic approach does not have the information needed to fix an overall additive constant in the entropy. So we arbitrarily normalized the trace by saying that the trace of the identity was 1, and that caused the entropy of the maximum entropy state to be 0. And that, since there was this constant lambda shift in the entropy is independent of rho. So all entropies were shifted by an additive constant. So the algebraic approach really only tells us about entropy differences. So it tells us that empty de Sitter space with the observer in equilibrium has maximum entropy, and it lets us measure all entropies relative to that. And if you normalize it so that the maximum is 0, the others are all negative. So insofar as we only use the algebraic approach, we can't do better than that. Then at the end of the lecture, I conjectured something which might be better than the no boundary. The algebraic approach fails to fix a constant in the entropy, but worse than that, in different places in the landscape of vacua, there'd be a different constant. So the algebraic approach doesn't even let you compare different space-times. So we'd like to do better, and my proposal for doing better was to define entropy as minus the relative entropy with the no boundary state. Now, you see, now there's no arbitrary constant, assuming you know exactly what you mean by the no boundary state. In the paper, I naively tried to normalize the no boundary state. The result was that no matter where you are in the landscape, all my entropies differ from Gibbons and Hawking by a constant. But if you have the courage to just say, take the no boundary state from the path integral and don't bother normalizing it, then actually you get the Gibbons-Hawking answer. Any other questions?
So, as I have understood that in the holographic setting,
yes.
like Strominger and one also showed that the de Sitter wave function or the Hartley-Hawking state or no boundary state is related to the non-Euclidean CFT correlators at Timelike future infinity.
Yes.
So by using this holographic dictionary, can we try to normalize the Hartley-Hawking vacuum?
Maybe. I don't know how to, but maybe. I won't say no to that kind of question.
Okay, this is maybe last question.
Okay, thank you. In this context, is this the only kind of observer for which I can recover the Bekenstein-Hawking?
I'm not going to say it's the only kind. It's what I was able to come up with, trying to make it. Well, originally we were just trying to make sense of what could be observed in de Sitter space. I didn't explain the CLPW paper in detail because there wasn't time, and then I approached it from a different angle, so I didn't need to. In the CLPW paper, we observed that if you don't include an observer and you impose the constraints, you're left with no operators at all. So we had to include, but that seemed physically sensible, because if there's no observer, why should there be an algebra? Then we had to include an observer so we could say something, and we included the simplest model we could think of, and it had nice properties.
The observer was constrained at the time, not limited.
It's an important question, since, for example, our civilization didn't always exist as far as we know. Well, not just our civilization, but as far as we know, our phase of the universe didn't always exist. So I don't have anything useful to say about that, but it's an important question.